Hello again, my name is Tim Baldridge. I'm a developer with Cognitect, and today I want to talk a little about a translation of a program I've done from Prolog to Clojure. Specifically, this program is a set of tutorials from the PyPy developers, and it's actually just a really clear, awesome example of how to write a tracing JIT and an interpreter in Prolog in the example. But I'll be translating this into Clojure. So I have the first tutorial here translated, and I want to do a little walkthrough through it and talk about it. So what we're going to do first today is build an interpreter for a very simple language. That language is represented here. Here is the data representation, this could maybe be an AST, for a function that raises a certain variable to the power of another variable based on a recursive algorithm. So when we come in here, these operations follow the same format. Its operation is the tag, and then we have the result variable to stick it into. We have the operation to perform, and then we can have either one or more arguments. In our case, same doesn't do anything. It's basically an identity function that assigns the argument to the result variable. So this is basically saying let res equal 1. And then we say if y, then we go to power recursive here. Otherwise, we go to power done. And this is pretty much not needed because y exists. It comes as an input when we call the interpreter. But it'll basically jump directly here to power rec. And then we say let res equal the multiple, or the product of multiplying res by x. Then we subtract 1 from y equals y minus 1. We compare to see if y is greater than 1, and if so, greater than or equal to 1, and if so, then we call again into power rec. And then when we're all finished, we go into power done, down here. And so in the tutorial that I'll link, this is done in Prolog. The interpreter is written in Prolog, and there's nothing wrong with that. It's just I like to do a lot of my programming in Clojure. But it just so happens that the algorithms they have don't really require a logic language, and it just really requires a sort of pattern matching. I may end up looking into putting it into core logic and see what sort of trouble I get myself in. But until then, let's just use core match and do some pattern matching. So here's the interpreter. It's extremely simple. And in fact, let's go up a little bit higher here and say we have a couple of helper functions. One says constant. If x is a symbol, then it's not a constant. Simple enough. And then we say resolve this argument in this environment. Now the environment is going to be a hash map of symbols to values. So when we say assign, when we have result is same 1, we're going to actually create a new hash map with 1 in that hash map assigned to res. So what we say here is if argument is a symbol, then if the argument is in the environment, then get the argument out of the environment. Otherwise, assert false could not resolve arg in environment. So we'll say, hey, we don't know what this variable was used before it was defined. Otherwise, if it's not a symbol, we'll assume it's a constant and we'll just return it. And that follows up here. If it's a constant, then it's not a symbol. So doop here takes multiple arguments and matches on the args. And this could be improved a lot, but this is the way that the code was written in Prolog, so I figured, hey, we'll just translate it pretty much directly. So if our op is same, then we take x and return x. If it's multiply, we take x times y, so on and so forth. Makes sense, right? It just takes the arguments to this operation and then pattern matches. And you can see how we could build this function in multiple different ways, but that's it for now. Blocks is going to be the current set of, it'll be the program, which will be a symbol and then the first argument in a block, or first instruction in a block. And we can jump to other blocks by looking in this dynamic variable. And code cache we'll use later, don't worry about that. So what we're going to do here is we are going to start by printing the environment on every step, and then we're going to match the instruction. And we're going to say, hey, okay, we have this instruction, and this instruction is going to be matched on. So in the simple case, we say if we have a result and an operation and one arg, and rest being the next instruction. If we look down at our code here, these are actually nested vectors on each one. The last slot in each vector is the next instruction. So if we just did last on these, we could go through each instruction. So op result arg rest. Then we're going to resolve the arg in the environment. We are going to have a return variable be doop, so we call into here of the operation from here and the arg. Our new environment is the environment with the result variable here, associated, and the arg, and then we recur to the environment, recur again with the new environment here, and rest being the next instruction. So that makes a lot of sense if you look at the code right here. So we see we are going to resolve one is a constant. We call doop with same returns the variable passed in, which is 1, and then 1 gets associated into the environment under the symbol name res, and we continue on to the next instruction, which is here. The second one here is exactly the same, but with 2 arguments, arg1 and arg2. We resolve both, continue on. Jump says, hey, this is an absolute jump. So go into our blocks dynamic variable, which is going to be an atom, pull out the block that we're jumping to, and then recur, because that's the value that we get out of this hash map is the first instruction, just as we saw here. So power rec would be another block, or power done, so on and so forth. And then we have if. And this is very simple once again. If we resolve test and environment and it's true, then we recur into the then block, and then recur into the else block, and then print and stops just says print line, and we resolve the arg in the environment, which is here. So the print and stop here, we print out res and we're done. So we just exit we don't recur in that case, we just exit. All right, so that should be pretty simple. So what we're going to do here is we're going to create a binding called blocks, which is our code here. We're going to create a code cache, which once again isn't used until later. And then we're going to call this interpreter. So what we say here is our starting block, this will be our start position, is going to be power, which is up here. And we're going to create a starting environment, which are our 2 args, x and y. So x, we're going to basically take... let's see here. We're going to multiply x by itself this many times. So if we execute this, because we have this print line, it prints out the entire environment on every step. But we see x and y are 10, and then we've assigned res to 1, res is now 10, and y is decremented, and each time that we recur here, slowly y decrements, and the value of the result goes higher and higher and higher until we get our final result. So that's pretty cool. And that's just the first step. And interpreters can be written multiple different ways, and this is nothing really new. Writing an interpreter like this is simple. But we want to do something a little bit different. We want to find a way of optimizing this code. And we want to do it in a way that allows us to make certain deductions about the code. So the first step in this tutorial, and the first step that we're going to take today, is what's called partial evaluation. And if you see here, there's one variable that never changes throughout this entire program. And that's this value 10. So it could be possible that we could evaluate parts of the program using a certain variable that will never change. Right? To say, hey, you know what, this variable is constant, and because we've made that constant, we can create a new program that's optimized as if that variable was constant. To do that, we need a few more helpers. So the first helper here is presolve. And this differs from the other resolve in one simple way, and that is we try to resolve it, but if we fail, we don't throw an exception, we just return the variable. And this will be, the reason why we need this is a little, it will make sense in a little bit. And then we have to forward declare an argument here. And then we have this wonderful function here called partial evaluation, or PE. Given an instruction and a partial environment, which will be an environment of things that we have already kind of deduced and figured out, we're going to execute this program. Now, when I say execute, it looks a lot like the interpreter we looked at before, but we're only going to evaluate things that we know the answer to. So constant folding is really what we're doing in this case, and a little bit of rewriting. So what this does is say, okay, if we have a one arg operation, and we know what that arg is, because it's in the environment, and that arg is a const. And let's look at p-resolve here again. If it's a not a symbol, we just return it. So if it's a constant, and we pass it in here, it'll always succeed, and we get the arg back. And so if it's a constant, then we say we're going to go ahead and do the operation and get the result. And then we're going to create a new environment that says, you know what, at this point, with this collection of environment variables and state of the program, we know that this value, that we know that, for instance, res is what we'll be looking at here. We know that res equals, let's say, 1. And then we're going to recur with the next part of the program. So we've basically said, hey, we know that the only input to this argument is a constant. And so we'll go ahead and run the operation. And then we'll update the environment to say, hey, we've executed this operation and here was the result. Now, if it's not a constant, then we have to remove the variable from the environment if it exists. And we are going to then do partial evaluation again, recurse up to here, and continue on with the next operation. And when we're done, we're going to rewrite this operation with the new tail. Now this part does consume stack, and I'm not exactly sure how I'm going to rewrite this so that with significantly large programs this doesn't blow the stack and create a stack overflow. But it works for our cases here. So the result of this is going to be a little more, let's continue on, and this will make a little more sense once we get to the end of the demonstration here. So if we have a 2-argument operation, we're going to resolve both of those. If they're both constants, we're going to do the operation, and then we're going to associate the result into the environment, and then recur again with that constant in the environment. If they're not both constants, then we continue on and create a new next instruction. So all of our children can be constant folded still, and when they update, we'll create a new instruction with our rest, or the next operation being that rest, the new rest, and we'll continue on. So what you can see here is if arg1 comes out to 1 and arg2 comes out to 2, and our operation is multiply, then both of these will be constants. We'll multiply 1 by 2, which is 2, and then we'll stick this as an environment and say, at this point, res or x or y is 2. Right. Okay, so jump is simple. If we come to a block, we continue to do our partial evaluation at the new block location with our current environment, and then update. So do PE will return a new block ID. If it's rewritten a bunch of code, it'll create new blocks of code, and we need to update our pointer to jump to that. And so we do that. Print and stop is the same sort of thing. We do a p-resolve and resolve and rewrite that instruction. That allows us to constant fold all the way up to the print. And then if is a little bit interesting here. So test then and else. We say if the value is in the environment and the value is known, so this is a constant, then we're going to just fold that. We're going to completely remove the if and replace the if with a jump, a absolute jump. If we know the value in the if, and there's no reason to do the comparison anymore. There's no reason to do the branch anymore, and we can replace the branch with an unconditional jump. If that's not the case, then we need to still partially evaluate our 2 children and possibly rewire our instructions there as well. Okay, so here's do PE. And what this will say, there's a little bit of caching that goes on here, and this gets a little bit fun. So we have this other thing called a code cache down here. And what this says is that for this partial environment, remember each time we modify, we create a new variable or remove one, we create a partial environment. For this partial environment and this block of code, do we know, let's see here, partial environment and code. If we know if we have a cache value for this partial environment and this block, then we're just going to return that. Otherwise, we're going to create a new one, a new block with a gensim, and we're going to swap that in and say, okay, for this block and this partial environment, here is the block you want to jump to next, and then we're going to partial evaluate that block, that input block here. We're going to partial evaluate the input block with the partial environment that we have, and then we're going to create the new block. So what this is doing basically is copying blocks. It says, you know what, we want a block that looks just like this, and we're about ready to partial evaluate it, but we need a place to put it. So that's what do PE does, is it kind of creates a new slot for a block, but does it in a way, and this is the key, does it in a way that if we recurse back around with the same set of values and parameters, we're not going to end up creating 20 different blocks. So it's kind of creating singleton blocks given the parameters and the source block, if that makes sense. If not, take a look at it a little bit more, it might make sense. So, all that being done, let's cut out this here. Okay, so what we're going to do is we're going to execute this do PE. And we're going to start at power. So we say, okay, with our code, and we have an empty code cache, and we say, we're going to execute the function power, and y is going to be set to 10. So y is a known variable already in this system. If we run this, we get start at PE block 45191. Well, what does that mean? Well, do PE, remember, returns the rewritten block. So it says, okay, I rewrote everything, and power is now replaced with this other block. Okay, so what do those blocks look like? So let's execute this. And we see, wow, we have a completely new set of instructions here. So it says start at 45207. So if we go to 45207, it just says jump to 45208. All right, 45208 says multiply 1 by x and sort in res, and then jump to 209. 209 says multiply res by x, and then jump to 210, which is up here. Now, and then we have multiply by x again, and again, and again, and again, and again. Well, wait a minute. What happened? Well, if you remember up here, y is this counter, right? Y starts at 10 and counts down. But we know the starting value of y is 10. Or in our case here, in this example, yeah, it's 10 here. So what this has basically done is taken all the ifs and everything and unrolled them into one long chain that just says, literally, take x and multiply it. Take the res and multiply it by x over and over and over and over again until you've done that 10 times. So we've removed all the jumps. Now these are still multiple blocks, but if we were actually going to emit this code, it would be very easy to just rip out the blocks and stick these into one big block, which basically is just the straight line code. So we've unrolled the loop, in essence. And we can put the code cache. So this is the code cache that was spit out. It says, so power rec with res of 1 and y with 10. This is the block it created and so forth. Okay, that's kind of cool. Maybe a little useless. But now, wait a minute. If we have blocks, we should be able to execute it, right? So we can execute blocks and say start at, we're going to start at the variable that we were given to start at and say x is 2 is our starting value. And if we run this, sure enough, we don't see any indication of y because y has been completely removed from the program altogether. It's been constant folded all over the place and removed. And so So yeah, what's kind of interesting is we can just modify this variable here to have any sort of values we want. And we've basically created an optimized function that takes whatever number we pass in and brings it to the 10th power. Now, I haven't tried this yet, but there's no reason we shouldn't be able to also put x in here. So if we say 10 to the 10th, and we shouldn't need anything in our environment here, we in fact get nothing and just get this output. And what type of code was created? Whoa! This is actually cool. I'm not faking this. I have never actually tried this before. This is pretty cool. Basically what we have are a bunch of jumps and then followed by print and stop with the value. That's actually kind of cool. And it's just a little bit of work then, of course, to go up here and to do this. I wonder if we could actually do that. Let's try. We could say let res equal do PE of block and environment. And then if first of res is, we're going to say jump, then we're just going to return res. Otherwise, we're going to return jump res. So if we execute this, we see start at 46527, 465, where's 527? 527, 28, nah, didn't work like I thought. I'm gonna have to look into that, figure out why that isn't happening. But it should be possible, I would think, to somehow get this to resolve to start block. So that we would just jump in, print and stop, and we've constant folded the entire program. I'll take a little more playing around with that, but maybe we'll cover that in the next tutorial. So where do we go from here? Well, this is the first part, and partial evaluation is done in almost every compiler. I mean, it's not even worth talking about, but this example is kind of cool. From the other tutorials, we can get more and more advanced. And what we'll get more into is, I want to start talking about a tracing JIT, where basically we execute code over and over and over. As we're executing code, we're analyzing the code. And after we have seen the same loop happen enough times, we stop the program and we begin tracing it and basically do something kind of like partial evaluation, but where only thing we do is record all the instructions that we're executing. And at that point, after we loop around once again, we take those list of instructions, we look at them, find some constant variables, set those as constant, and then partially evaluate that trace, and then run that optimized trace. So if you want to see the whole set of tutorials, I'll put a link to it in the bottom. It's on the PyPy blog. Great stuff. But this is just the first one, and it's something I've been working on the past couple days to kind of see what sort of trouble I can get into playing with interpreters and partial evaluation and closure. So thank you very much for watching.